Hi all, I'm going to take you through this assessment task 1 for chemistry year 11. Okay, so here we have what's the electron dot configuration for the chlorine atom. That's in group 7. Now because it's the atom, it has to have, as opposed to the ion, we want to check 1, 2, 3, 4, 5, 6, 7 valence electrons. 7 would be correct. Right, so electron configuration, well there are, let's count the electrons, 2, 4, 9. So that makes, if it was the atom, it would be fluorine. Okay, so it's a fluorine atom. Can't be the chlorine ion or chlorine atom because there's that would need a whole lot more electrons. The fluorine ion would be 2p6. That makes it the fluorine atom. Right, so what's happening here? We've described the process. Well, we've got a metal and a non-metal. That forms an ionic bond. Okay, they're hanging out together because of the electrostatic forces. So ionic would be correct. So 2 electron pairs shared between 2 atoms. You know, underline the keywords if you need to. So let's just test it out. So 1, 2, 3, 4, 5, 6 for oxygen. 1, 2, 3, 4, 5, 6 for oxygen. That's not enough. They need 8 each. So if we share them, that's 2, 4, 6, 8. 2, 4, 6, 8. And so that's double bonded with 2 shared. Okay. Have a look here. What's the name of this? That would be dinitrogen pentoxide. Okay, perfect. What about this one here? We've got how to identify PbO with a name, as opposed to you might have another lead oxide which is Pb2O. Okay, so we have to be able to distinguish the difference between these. So PbO must have a valence of 2, so we say 2 lead 2 oxide is going to identify PbO as the name. It's not good enough just to say lead oxide. Okay, here we have, they're asking us which compound would have the highest boiling point or melting point. Right, well that's the one with the stronger bonds, which in this case, this is a giant covalent network. Covalent bonds are generally stronger than ionic. So you would say that this one on the left, because it has stronger bonds, has a higher melting point. But I'd accept if you related this question to the strength of the bonds and gave that as a reason for having a higher melting point, I'd pay that. Here we go. We have the image below. So we've got a sea of electrons because they're irregular. And so this is a metallic bond. Okay. Name of the type of bond labeled A and B. Here we have a covalent bond, intramolecular, and here we have an intermolecular. Now it's not hydrogen because FON is not involved, and therefore it's dipole-dipole, so B would be your answer here. Thank you. Next. Name the shape of the molecule that this will have. Okay. Now considering that all these arms are trying to repel from each other in 3 dimensions, so this forms a tetrahedral shape. Electronegativity of an element is the measure of the element. So FON on the periodic table, it's increasing as we go to the right because fluorine's the most electronegative, and that's increasing as you go up. So increases to the right and decreases down a group would be your answer. Next one, identify the correct Lewis structure. So you can test it out. Nitrogen's got 5, 1, 2, 3, 4, 5. Carbon's got 4, 1, 2, 3, 4 electrons. Hydrogen's got 1, so they join up. And if these join up, we've got 2, 4, 6, 8, 2, 4, 6, 8, and 2, and that would be the correct one here. Which atom would form a triple bond? Again, draw it out and just test it out. So nitrogen with the electron pair, 1, 2, 3, 4, 5 in total. 0, 5 with 3 triple bonds will make that 2, 4, 6, 8. 2, 4, 6, 8. Okay, so nitrogen's the answer. There can't be hydrogen. Here's a harder question for the paper. Now, each atom has a double bond at the end, an electron pair, and a single bond between each one. So it has to be the same atom. And if you test nitrogen, okay, because you're looking for 1, 2, 3, 4, 5, it could be nitrogen or phosphorus, for example. And then they could all join up in 3 dimensions. That way it would be tetra nitrogen or tetra phosphorus. As possible answers. I've done this one already. Which of the following molecules has a net dipole moment? Carbon dioxide is nonpolar. Carbon tetrafluoride is nonpolar. Oxygen is nonpolar. The only one that's polar is ammonia. And if you add up all these dipoles, you get a net dipole moment, which confirms that. What is a V-shaped molecule? Okay, it's something like water. Okay, so you could give the H2O would work, or H2S, dihydrogen sulfide is another one that we've looked at. Okay. The weakest of all the intermolecular forces is the dispersion forces. The dispersion forces. Butane, which is a balanced molecule. Okay, it's non-polar, so it hasn't got anything needed for hydrogen bonding. It's not polar, so intermolecular means it must be dispersion. Which would have the highest boiling point? Well, if you have a look, they're both got the same number, 1, 2, 3, 4 carbons here, and the hydrogens. So I mean, they're both non-polar. So so dispersion forces are going to be responsible. But which one of these two will have the largest dispersion forces? Well, the one with the greatest surface area, you'll get a bigger differential of the charge on the atom. So that would be a dispersion. Okay. Water, when compared to a similar substance such as H2S, has a higher boiling point because, well, H2O has this special ability to do hydrogen bonding. If you think back to the graph we looked at, it was due to that hydrogen bonding that led to have a much higher boiling point, whereas H2S does not have hydrogen bonding. So you can, no, that can't be it, because H2S can't have hydrogen bonding. H2O has weaker hydrogen bonds, no, as compared to, so H2S doesn't have any hydrogen bonds, so this must be the only answer. Name the intermolecular bonds here. So we're looking at what's going on here. Well, that's between a dipole and an ion. So it's called an ion dipole bond. So give it the chemical formula of 2 allotropes of oxygen. So O2 and O3. correct. Now, perform an experiment by pouring liquid mercury onto, so you got one meniscus which is upwards and the other one which is down. It's quite amazing phenomenon just to look at it. Why does it do that? Well, one, there are water, because the silicon dioxide in the glass allows hydrogen bonds to form between the water and the silicon, so it sticks to it, so it's grabbing onto it, whereas that's not present in the between the metal and the glass. The other factor is that metallic bonds themselves are very strong as well, much stronger than hydrogen bonds, so that is going to have a much stronger surface tension, causing that. So the two correct answers here, although I didn't indicate that I wanted to answer strongly, so I'll be happy just to get either of these two answers. Hydrogen bonds are stronger than, oh no, that's not it. Metallic bonds are stronger than hydrogen bonds, and then there's all hydrogen bonds are present between the water and the glass. But ideally both of those two answers. Okay, so I'll pay that one. So here we have a model of water and the intermolecular forces between them. Now what happens at the surface is that in the middle, all these forces balance out. Okay, so there's net and zero net force due to the intermolecular forces, but on the surface here, this is being pulled inwards, this is being pulled that way, these cancel out, so the net force is inwards on the surface. So molecules below the surface, so it would be this one here, B, correct. Polar molecules are best described as, well, so this is a good tricky question here. Let's go through them all. So let's try, I don't know, carbon dioxide. Okay, it's got different atoms, but they're balanced. Okay, so it's non-polar. So it's not this one. Are molecules that are symmetrical? Well, no, molecules that are symmetrical, such as this one, are again non-polar. So it comes down to these two. Now, it is true that oxygen, when bonding with hydrogen, say for instance water, that's a good classic example of a polar molecule. Polar molecules, with when the central atom does have electron pairs, yes, it's true that they are polar, but it doesn't mean every molecule with lone pairs is a polar molecule. For instance, neon is a molecule with lone pairs on it, and it is not polar. There are other ones that occur as well. Okay, so you can have like an arrangement where you have electron pairs, something like that. So in this case, it is not polar because it's symmetrical. But, so the best way to describe that is all molecules that have a net dipole moment are polar. Lastly, alkanes, so this is similar to this question here. So as the carbon chain gets longer, now, so these are the hydrogens. What's happening here? Well, as the chain gets longer, the boiling points increase, okay, in this direction. As the chains get longer. So why is that? Well, it is because of dispersion forces, but not only that, it's also harder to get these moving because they're heavy. The bigger the molecule, the heavier it is. So there's two factors going on. So the boiling point increases due to dispersion forces and increasing mass. Right. Oh, there is one more. So this is another tricky question. Which ones are capable of hydrogen bonding? Well, you got to look for F, O, and N. That must involve those atoms with a hydrogen bonded to those. Okay. And the other thing is that, it must involve these with a spare electron, lone electron pair, and it must also, the hydrogen must also be bonded with a FON. So let's have a look. No FON, no FON, N with the lone pair, and the hydrogen connected to that. So that has both factors that are needed. So this is one. FON, you can write it down like this. Okay, FON, yes, and the hydrogen is connected to the O. Okay, so that's the second factor. FON, true, and this is it has the O here, but the hydrogen is not connected to the FON. So this is not going to be able to, this is just not positive enough. Okay, because the carbon doesn't have a strong enough pull. So it's not classified as hydrogen bonding. And that is not FON. So the only two are the middle ones. Okay, so that's it.